Okay, so we're diving into distributional reinforcement learning today. Have you ever wondered if there's a way to look beyond just the average expected reward in reinforcement learning? What if we could capture like the whole spectrum of possibilities?
Yeah, the full range of risks and rewards.
That's where distributional reinforcement learning comes in.
That's right. Distributional RL is all about moving from a single point estimate of expected value to looking at the entire distribution of possible returns for an action.
Okay.
Instead of just asking, like, what's the average reward I'll get?
Yeah.
We ask, what are all the possible rewards I could get, and how likely are each of them?
So instead of just knowing the average, we're getting a much richer picture, like almost like a map that shows not just the main highway, but all the back roads and side streets too, and how often each one gets congested.
Exactly. And having this full picture can lead to some really interesting possibilities, especially when it comes to building AI agents that can handle risk and uncertainty in more sophisticated ways.
Yeah, that sounds really intriguing. So let's start with something familiar. We both know the classic DQN, the deep Q network algorithm that learned to play Atari games by maximizing expected reward. How does distributional RL build on that foundation?
Well, one of the early breakthroughs was C51, which stands for categorical 51. It's a clever modification of DQN that instead of just estimating a single expected value, represents the value distribution using 51 categories.
What?
Think of it like dividing the range of possible rewards into 51 buckets, and then figuring out the probability of the reward falling into each bucket.
It's like a histogram, showing the distribution of potential rewards. And this seemingly simple change led to better performance.
Yes, C51 showed some remarkable performance gains. In some Atari games, it was up to 2.5 times better than the original DQN.
Wow. 2.5 times better.
That really showed the power of considering the entire distribution, not just the average.
That's a huge jump. So what came next? How did researchers push distributional RL even further?
They started exploring different ways to represent and learn these value distributions. One approach was QR-DQN, which uses quantile regression to estimate the value distribution.
Okay, quantile regression. I remember that from my statistics classes. But Can you remind me how it applies here?
Imagine you want to know not just the average reward, but also what reward you can expect 75% of the time or 90% of the time. Quantile regression helps pinpoint those specific values within the distribution, giving you a more detailed picture.
Okay, that makes sense. So instead of just knowing the average, we can pinpoint key percentiles within the distribution. How does QR-DQN actually use this to learn?
It aims to minimize the Wasserstein distance between the estimated quantiles and the true distribution, which we get from the distributional Bellman equation.
Wasserstein distance. I'm not familiar with that one.
Think of it as measuring the effort required to transform one distribution into another. Imagine you have two piles of sand, and you want to reshape one to look exactly like the other. The Wasserstein distance would tell you how much work is needed to move the sand around.
So we're trying to make our estimated distribution match the true distribution as closely as possible. And the Wasserstein distance tells us how far off we are.
Exactly. And QR-DQN, using this approach, achieved state-of-the-art results, even beating C51 in some tasks.
It's like a race to find better and better ways to represent these complex distributions. Where did that race lead to next?
It led to the development of IQN, or implicit quantile networks. While QR-DQN uses a fixed number of quantiles, IQN takes a more flexible approach. It learns a continuous function that can represent any quantile you ask for.
So instead of having a limited number of points in the distribution, we can now estimate any point we want.
It is.
That sounds incredibly powerful.
This function is called the quantile function. It maps probabilities to values. Want to know the reward at the 10th percentile? Just plug in 0.1 and the function gives you the answer.
That's really impressive. So how does IQN learn this function?
It uses a clever technique involving sampling. It takes samples from a simple distribution, like a uniform distribution between 0 and 1. These samples represent different quantiles. Then, along with the state and action, these samples are fed into a neural network, which learns to map them to the corresponding values in the true distribution.
So we're training the network to answer quantile queries. We ask, what's the reward at this quantile? And it learns to give us the right answer.
Exactly. And this seemingly simple idea leads to incredibly powerful results. IQN almost matched the performance of Rainbow, an algorithm that combines several state-of-the-art techniques on top of C51.
Wow, almost as good as Rainbow. And with a much simpler approach. Did anything else stand out about IQN's performance?
There's one fascinating detail. Even when researchers use just one sample per update, IQN still significantly outperformed DQN.
Interesting.
It suggests that learning this continuous representation of the entire distribution, even if you're only using a small part of it at any given time, is fundamentally more powerful.
That's really intriguing. It hints that there's something special about learning the full quantile function, even if you're not using all of it at once. It's like having a detailed map helps you navigate, even if you only travel on a small portion of it.
That's a great analogy. And you know what's even more mind-blowing? There's evidence that our own brains might be using something akin to distributional RL.
Wait, really? Our brains?
Yeah.
Tell me more about that.
A recent study published in Cell looked at dopamine neurons, which are crucial for reward processing in the brain. They found that these neurons don't just respond to the average reward, but exhibit diverse response patterns that seem to represent different quantiles of the reward distribution.
So it's like different dopamine neurons are specialized for different parts of the reward distribution. Like some are tuned to the high reward tail, while others are more focused on the low reward tail.
Exactly. And this structured heterogeneity suggests that these populations of neurons might be working together to create a neural representation of the entire reward distribution, much like the algorithms we've been talking about.
That's incredible. Our brains might be doing something similar to these cutting-edge AI algorithms. It's amazing to think about the connections between artificial intelligence and neuroscience.
It truly is a fascinating link. And it raises all sorts of interesting questions about how we can use these insights to build even more sophisticated and powerful AI systems.
This is seriously mind-blowing stuff.
Hmm.
But before we get too carried away, I want to take a step back and ask a practical question. If distributional RL is so powerful, why isn't it more popular in practice?
That's a great question, and it's one that researchers are still grappling with. There are a few reasons why distributional RL hasn't quite hit mainstream adoption yet.
I'm all ears. Let's hear those reasons, because this all sounds incredibly promising. But it's also important to understand the practical challenges.
One reason is the added complexity. Modeling distributions is inherently more complex than modeling single values. It requires more sophisticated algorithms, more computational resources, and often longer training times. It's a trade-off between the richness of the information you gain and the computational cost of obtaining it.
Right, it's like choosing between a standard definition image and a high-resolution one. The high-resolution image has more detail, but it also takes up more storage space.
Exactly. And another challenge is that while we've made great strides in learning these rich value distributions, we're still figuring out the best ways to use that information for decision-making. Most research still relies on just the mean of the learned distribution.
It's like we built this incredible high-resolution map, but we're still just using it to find the shortest average route. We haven't fully tapped into its potential.
That's a perfect analogy. And that brings us to one of the most exciting opportunities in distributional RL, developing truly risk-aware policies. Instead of just maximizing average reward, these policies can take advantage of the entire shape of the value distribution, factoring in risk and uncertainty.
We touched on risk-sensitive policies earlier. Can you give me like a concrete example of how this might work in practice?
Imagine a self-driving car. In some situations, like on a highway, it might be acceptable to take calculated risks, such as changing lanes quickly to overtake slower vehicles. But in a school zone, safety is paramount, even if it means driving slightly slower.
Right. The context matters. So how could we design an agent that can dynamically adjust its risk tolerance based on the situation?
That's where things get really interesting. Instead of having a fixed risk preference, we could design agents that learn to adapt their risk tolerance based on the environment and their goals.
So the self-driving car could learn that in a school zone, a risk-averse strategy is optimal, while on the highway, a more risk-neutral strategy might be better.
Exactly. And this learning could happen in real time as the agent interacts with the world, constantly adjusting its behavior to maximize performance while managing risk.
That level of adaptability would be incredibly powerful. What other applications of risk-sensitive policies come to mind?
Think about applications in finance. A trading agent that's aware of the entire distribution of potential returns could make much more sophisticated investment decisions, balancing risk and reward to maximize long-term gains.
It could avoid those high-risk gambles that could lead to catastrophic losses, even if they promise high average returns.
Precisely. Or imagine an AI controlling a power grid. By understanding the full distribution of energy demand, it could make more informed decisions about energy allocation, reducing the risk of blackouts during peak times.
These are some seriously high-stakes examples. It's becoming clear just how impactful distributional RL could be in many real-world applications.
Absolutely. And there's another area I find particularly intriguing: leveraging distributional RL to create agents that can reason about uncertainty more effectively.
Reasoning about uncertainty is crucial in any complex real-world environment. How does distributional RL help us achieve that?
Remember how these value distributions capture not just the expected reward, but also the spread of possible rewards? This spread can be interpreted as a measure of the agent's uncertainty about the outcome of its actions.
So a narrow distribution means the agent is quite certain about the outcome, while a wider distribution implies more uncertainty.
Exactly. And this uncertainty information can be incredibly valuable. For instance, an agent exploring a new environment could use the width of the value distribution to guide its exploration, focusing on areas where there's more uncertainty.
That's a clever strategy. Instead of randomly exploring, the agent could prioritize areas where it has the least information, potentially leading to faster and more efficient learning.
Precisely. Or imagine an AI system interacting with a human. By understanding its own uncertainty, the AI could be more transparent about its limitations, explaining its reasoning and highlighting areas where it needs more information.
That kind of transparency would be crucial for building trust between humans and AI. It's not just about making the right decision, but also about explaining your reasoning, especially when there's uncertainty involved.
Exactly. Distributional RL gives us a framework for quantifying and communicating uncertainty in a meaningful way.
This all sounds very promising. But as with any cutting-edge research area, there must be some challenges and open questions.
Of course. One challenge we touched upon earlier is developing more sophisticated methods for utilizing the entire value distribution, not just relying on the average.
We need to go beyond simply having a detailed map and figure out how to use all of its information to navigate effectively. What other challenges are there?
Another is the computational complexity we mentioned earlier. Modeling and learning distributions is computationally demanding, and this becomes even more pronounced as the environments and tasks become more complex.
Right. We're essentially working with an entire function, not just a single number. So finding ways to make distributional RL more efficient and scalable will be key.
Absolutely. And there's also the ongoing challenge of finding better representations for these value distributions. We discussed C51, QR-DQN, and IQN, each with its own strengths and weaknesses. But there's always room for improvement.
It seems like a perfect playground for innovative AI and ML researchers. What are some of the other promising directions you see for future research?
One exciting direction is exploring the connections between distributional RL and other areas of machine learning, especially in deep learning and generative modeling.
You've piqued my interest. What could we borrow from those fields?
Well, we already use neural networks extensively in distributional RL, but imagine leveraging techniques from generative modeling, like variational autoencoders or generative adversarial networks, to represent and learn value distributions.
Generative modeling is about building models that can generate new data that resembles the data they were trained on. How does that apply here?
Instead of generating images or text, we could use generative models to generate samples from the value distribution. These samples could then be used to estimate properties of the distribution, like its mean, variance, or specific quantiles.
That's fascinating. So we could use these powerful generative models to capture the complexity and variability of reward distribution.
Exactly. And this connection between distributional RL and generative modeling could be mutually beneficial. Generative models might offer more flexible and expressive representations for value distributions, while distributional RL could provide new objectives and evaluation metrics for generative models.
I'm starting to see how these different areas of machine learning could come together to create even more powerful and sophisticated AI systems.
It's a truly exciting time to be working in this field, and as research in distributional RL continues to advance, I have no doubt we'll see even more groundbreaking discoveries and applications. It's a field with immense potential for innovation and impact.
I'm completely hooked. This deep dive has been an incredible journey, opening my eyes to a whole new way of thinking about reinforcement learning.
I'm glad to hear that. And before we wrap up, I think it's important to highlight the key takeaways for our listeners.
Absolutely. Let's do that. For those of you listening, if you've been working with traditional RL, the biggest takeaway is that distributional RL offers a completely new perspective. It's about moving beyond just expected values and embracing the entire distribution of possible rewards.
That's right. It's a shift from asking, like, what's the average outcome, to asking, what are all the possible outcomes and how likely is each one? This allows us to build agents that can handle risk uncertainty and complex trade-offs much more effectively.
We've seen how distributional RL can lead to significant performance gains, especially in challenging environments. And we've discussed how it opens up the door to exciting new possibilities, like risk-sensitive policies and uncertainty-aware agents, which could have a huge impact on fields like robotics, finance, and healthcare.
And we can't forget the fascinating connection between distributional RL and how our own brains seem to process rewards. It suggests that we're on the right track, and that there's still much we can learn from the incredible efficiency and adaptability of biological systems.
It's a truly inspiring thought. But before we wrap up, I want to leave our listeners with something to ponder, a thought that builds on what we've discussed, but takes it a step further.
I love those thought-provoking endings. What do you have in mind?
Well, we've talked extensively about modeling the distribution of rewards. But what if we broadened our focus and started thinking about modeling the distribution of outcomes?
Outcomes? That's an interesting idea. What do you mean by that specifically?
Rewards, as we typically define them in RL, are often single scalar values that the agent aims to maximize. But in real-world scenarios, the consequences of an action are often much more complex and multifaceted.
I see your point. A self-driving car, for example, might care not just about reaching its destination quickly, but also about minimizing fuel consumption, ensuring passenger comfort, and of course, prioritizing safety above all else.
Exactly. And those objectives might sometimes conflict with each other. So instead of just maximizing a single reward signal, what if we built agents that could reason about the entire distribution of potential outcomes, taking into account all those different factors?
That would be a major step forward. It would require us to rethink how we define and represent objectives in RL, moving beyond simple rewards to richer representations of what we truly want our agents to achieve.
It's a challenging but incredibly exciting direction. And I think it perfectly captures the essence of distributional RL. It's about embracing complexity, acknowledging uncertainty, and building AI systems that can navigate the real world with a deeper understanding of the full range of possibilities.
I couldn't agree more. It's about building AI that's not just intelligent, but also wise, capable of making decisions that are not just optimal in a narrow sense, but also robust, adaptable, and aligned with our values.
Well said. It seems like we've only just begun to explore the potential of distributional RL, and I'm eager to see what the future holds for this fascinating field.
As am I. This deep dive has been incredibly insightful. Thank you for joining us on this journey into the world of distributional RL. We hope you've gained a newfound appreciation for the power of looking beyond expected values and embracing the full spectrum of possibilities.
And for all the researchers out there, we encourage you to keep exploring, keep experimenting, and keep pushing the boundaries of what's possible in AI. Who knows what amazing breakthroughs you might uncover. Until next time, happy deep diving.